Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we are discussing how to calculate molecular mass. We have a couple of different types of problems presented today, but let's look at the first set. It says calculate the molecular mass of the following compounds. We're given two different types of compounds, nitrogen dioxide and propane. We're going to start off with nitrogen dioxide. So, knowing how to determine what the chemical formula of these compounds is very important. So this one's relatively easy. There's nitrogen, and then dioxide means two oxygens. So the formula is NO2. The next step in calculating the molecular mass will be to find the masses of each species. So from our periodic table of elements, we can find the molar mass of any given species, which is exactly what we're needing. So for the molar mass of nitrogen, we're given 14.01 grams per mole. For the molar mass of oxygen, from our periodic table, we're given 16.00 grams per mole. And then it's just simply a matter of adding them all up. You can go whichever is your preference. You can either add one nitrogen and then add to it one oxygen and then another oxygen, or you can do what is conventional and generally easier, which is to say, in order to find your molecule's mass, you calculate it by doing the one nitrogen in this case, and then add to it two oxygens. But instead of writing each oxygen out, you just put a 2 in front because you're going to multiply 2 times 16.00 grams per mole. And once you've done the arithmetic out, you'll find that the molecular mass of nitrogen dioxide is 46.01 grams per mole. And that's it. That's all there is to it. Fairly simple, fairly straightforward. From there, we can be given the mass of nitrogen dioxide used, or the number of moles used, and use that value to calculate its complementary value. But for now, let's just keep moving forward. Next one is propane. Propane is listed in your charts in the book, but just so that you know, pro is the prefix for organic molecules, or hydrocarbons specifically, that indicates that there's 3 carbons. So you'll be looking for the molecule with 3 carbons, and then the H will always have double, in this case, at least with propane, will have double the number of carbons and then add 2 to it. So it'd be C3H8, because 3 times 2 is 6, and then add 2 would make it 8. Then it's just a matter of finding the molar mass of each species. The mass of carbon would be 12.01 grams per mole. And the mass of hydrogen is given as 1.008 grams per mole. Again, this is all from your periodic table of elements. And then you just set up your arithmetic series. So you have the mass is equal to 3 times the mass of carbon, which would be 12.01 grams per mole. Always remember your units. And then add to that 8 times 1.008 grams per mole for the hydrogen. And your molecular mass ends up being 44 0.09 grams per mole. So for every 1 mole of propane should weigh 44.09 grams. Let's look at some different types of problems that are asking for specific instances of molecular mass. So the first one asks, how many moles of butane are in 7.06 grams of butane? Butane, again, the bu is indicative of 4 carbons, and 4 times 2 is 8, plus 2 is 10, so C4H10 is butane. So we start off by determining the mass of carbon and the mass of hydrogen. Well, we were just given that before. We know them to be 12.01 grams per mole and 1.008 grams per mole, respectively. So let's skip that step for now, and we're just going to go ahead and calculate the molecular mass of butane. So the mass is equal to 4 times 12.01 grams per mole plus 10 times 1.008 grams per mole, which gives us a total molecular mass for butane of 58.12 grams per mole. That's only half the problem, though. We found the molecular mass, but we know how many, we're trying to find how many moles are in 7.06 grams. So the next step is simply dimensional analysis. You start what you're given, so 7.06 grams times a conversion of your molecular mass. So in this case, we want the moles on top. So 1 mole, for every 1 mole of butane, we have 58.12 grams. And you'll note that grams and grams cancel each other out, and we're left with moles, which is exactly what we wanted. So when you do the arithmetic out, you'll find that the answer is 0.121 moles. Again, looking at the significant figures, we have 3 significant figures as our least amount in the dimensional analysis, and that's what we ended up with. So that would be the correct answer. The next problem, and the final problem in this set, it asks how many hydrogen atoms are there in 26.5 grams of toluene, and the chemical formula for toluene is given as C7H8. So again, I'm going to presume that you already know what the molar mass of hydrogen and carbon are, because we've researched it in our periodic table. So from here, we're just going to calculate the molecular mass of toluene to start out. So for the mass, we know that it's 7 carbons, so 7 times 12.01 grams per mole, plus 8 times 1.008 grams per mole. And from that arithmetic, you'll find that there is, the molecular mass is 92.13 grams per mole. Pretty straightforward. Now, you have to note specifically what they're asking. They are asking how many hydrogen atoms are in 26.5 grams of toluene. So they're not asking how many toluene molecules, they're asking how many hydrogen atoms. And that's going to be very important when we set up our dimensional analysis. So let's get started with that. Dimensional analysis always starts off with our given. So 26.5 grams is our given. Then we want to convert that to moles so that we can eventually use Avogadro's number to bring it to atoms, correct? So for every 1 mole of toluene, there are 92.13 grams. So grams and grams cancel each other out. Let's put a little signifier on the mole, though, and you'll see why in a minute. We're going to put a little T for toluene. Then we're going to multiply this, recognizing that we need the atoms of hydrogen, not the number of molecules of toluene. So for every 1 mole of toluene, we actually have 8 moles of hydrogen, mole sub H. And we know this because of this little subscript 8 on the C7H8 molecule. So now we have the moles of toluene, and the moles of toluene have canceled each other out. And we now have moles of hydrogen only. Then we can use Avogadro's number. 6.022 times 10 to the 23rd atoms for every 1 mole, in this case, of hydrogen. And you'll note that moles of hydrogen and moles of hydrogen have now knocked each other out. So we're only left with atoms. And that's exactly what we want to have. You have to be very careful about what they're asking, because I'm sure there will be exams where it'll say something exactly like this with the intent that somebody is going to leave it in moles of toluene and end up getting the incorrect answer. So you really have to be certain of what it is that you're looking for. Once you've done the arithmetic out, you will find that the answer is 1.39 times 10 to the 24th power atoms. And that's it. And it has 3 significant figures, which matches the 3 significant figures in the given value. You could make the argument that 8 moles of hydrogen or 1 mole of toluene is technically 1 significant figure, but because that's used as a relational, we don't pay attention to it. The big thing to remember is that you're dealing with the given value as only having 3 significant figures.